Welcome to the talk. Today I'm going to talk about our paper, Bayesian repeated zero-sum games with persistent state with application to security games. This is based on John Roker, Vincent Connizer, and Shardin Dugby. So it's well known that private information can give an agent a strategic advantage in the game. However, taking the advantage of private information is usually complicated, especially in repeated games. This is well illustrated in the famous movie, The Imitation Game, in which the British intelligence successfully cracked the Enigma code. However, they chose not to add on some information in order to preserve its informational advantage. Intuitively, in this game, the agent with private information is facing two choices. The agent can choose to explore the information now. However, such an action may reveal the information to the opponent and hurt the agent's long-term utility. On the other hand, the agent can choose to save the information for the future. So the main question we would like to answer in this paper is how to play in repeated games with private information. So let's take a look at an example. In this example, we have 3 banks and 2 bags of money. And we are in a Bayesian setting, so that these 2 bags of money are distributed uniformly at random to these 3 banks, such that each bank can hold at most 1 bag of money. And we have 2 players. One is the soldier, also known as the defender, whose objective is to defend the money from the thief. And we have the attacker, the thief, whose objective is steal the money. And in this game, the soldier has informational advantage, so that the soldier can see the actual realization of the allocation of the money. Moreover, the utility of the thief is the following. So the thief successfully attack a bank if the bank is undefended with money. So let's see what happens if this game has only 1 round. So actually, the optimal strategy for the soldier is quite straightforward. So after observing the allocation of the money, the soldier will defend each of the 2 banks with money with probability 1/2, and he will not defend the bank without money. With this strategy, it will make each bank look the same for the thief. So from the perspective of the thief, each bank will have probability 2/3 to have money, and conditional on the bank having money, it is defended with probability 1/2. As a result, no matter which bank is attacked by the thief, the expected utility of the thief is always 1/3. Okay, let's see what happens if this game is repeated. So can the soldier use the same strategy as before? So for example, if the allocation of the money is that they are allocated to the first 2 banks, so can the soldier repeatedly defend the first 2 banks each with probability 1/2? It turns out that this is not a good strategy, because after a few rounds, the thief can learn something. The thief can learn that, okay, the bank that is never defended has no money. As a result, the thief can choose to attack one of the other 2 banks uniformly at random. In this case, the expected utility of the thief will increase to 1/2. So what should the soldier do in this case? Intuitively, the soldier should still defend the bank without money sometimes to mislead the thief. So in this way, the soldier will give a signal to the thief that, okay, now all banks may have positive probability to have money. And in this way, maybe defending a bank without money may benefit the soldier. So from now on, we are going to develop a principal way to implement this intuition. And before that, let me introduce some notations and game theory basis. So the base game we consider is the Bayesian zero-sum game. So in a Bayesian zero-sum game, so first of all, the distribution of the states is chosen by the nature. So the distribution is denoted by P. And then we have 2 players, the informed player, also known as the leader, and the uninformed player, also known as the follower. So the informed player can learn the state of nature, while the uninformed player does not know the true state of the nature. And after the state is sampled, and the informed player learns the state of nature, Then both players made their decisions about their strategy simultaneously, and then they play their strategy and earn their payoff. Now in this game, the payoff depends on both players' strategy as well as the state of nature. And we are in a zero-sum game, so that the summation of these two players' strategy would be 0. And we are going to make the Bayesian zero-sum games into a Bayesian repeated game with exogenous states with two adjustments. First of all, we will make the state persistent, in the sense that the state is also simple once, but the state will remain the same throughout the entire game. And we also made this game repeated, so this game will have multiple rounds. And in particular, we focus on Bayesian repeated games that is infinitely repeated. And the objective of each player is to maximize their average utility per round. We also made one more assumption, that is the follower can only learn her payoff in the end of this repeated game. We made this assumption because if the follower can learn her payoff during the gameplay, then the follower may be able to reconstruct the state of nature by her payoffs. And actually, all these assumptions are standard in the literature. So the first result we saw in this paper is a reduction from multi-round game to a single-round game. So we show that actually the Bayesian repeated games with exogenous states is equivalent to public signaling game. And in particular, public signaling game is a one-shot game. And this result was also shown by Allman and Marshall in 1995. And our main technical contribution is that we made this equivalence algorithmic. So what is public signaling game? So in public signaling game, we have one more player in addition to the leader and the follower. And in this game, instead of the leader learning the state of nature, the principal learns it. And the principal's objective is to optimize the leader's utility. In order to do so, the principal will commit to a public signaling game before she learns the state of nature. And after that, she will learn the state of nature and then draw a signal from the signaling scheme. And then the principal will send the signal to both players. So that in the public signaling game, the only information that is known by the leader and the follower is the signal. Neither of them know the true state of the nature. After receiving the signal, the leader and the follower can compute the posterior according to the signal and then place the optimal strategy for the induced zero-sum game from the signal. Okay, to make this more concrete, let's take another look at our example. So in our example, basically there are 3 different states of nature depending on how the monies are allocated. This money can be allocated to the first 2 bands, the last 2 bands, or the first and the third band. So if the money are allocated to the first 2 bands, denoted by the tuple 1, 2, then the optimal signal scheme will send the signal sigma 1 with probability x and send the signal sigma 2 with probability 1 minus x. Here, the ratio between x and 1 minus x is exactly the golden ratio. And for the other scenarios, for example, if the allocation of the money is to the first band and third band, then the signal scheme will send signal sigma 1 with probability 1 minus x. And on the other hand, if the allocation is to the last 2 bands, then the signal sigma 1 is not sent. So let's try to take a look at the posterior when the signal is sigma 1. So given the signal sigma 1, we can compute its posterior very easily because the prior is uniform. So basically with probability x, the allocation is 1, 2, and with probability 1 minus x, the allocation is 1, 3. So basically we know that with probability 1, there is a bag of money in the first bank. And with probability x, there is a bag of money in the second band, and with probability 1 minus x, there is a bag of money in the last bank. So given this posterior, we can develop the optimal strategy for the defender. So basically, the defender will defend the first band with probability x, and then defend the second band with probability 1 minus x. The defender will not defend the last bank. So now in this way, the defender actually equalizes the utility for the fifth of all these 3 banks. So if the fifth attacks the first bank, then he will succeed if and only if the defender is defending the second band. So that's with probability 1 minus x. And we can verify that no matter which bank is attacked by the attacker, the attacker's utility is always 1 minus x. Okay, for the other two signals, actually the posterior are identical to the signal sigma 1 up to symmetric. As a result, the soldier's optimal strategy is also identical up to symmetry. Okay, now we have the optimal signaling scheme. Then we are going to use this public signaling scheme to construct the optimal strategy for the leader. So after learning the state of nature, the leader will invoke the optimal public signaling scheme. And then to draw a signal from the signaling scheme. And then with that signal, the leader will play the optimal strategy according to that signal repeatedly. So in this way, we can see that the only information that can be learned by the follower is the signal, because the leader repeatedly play the same strategy again and again. And this strategy is induced by the signal. As a result, since the only information that can be learned by the follower is the signal, then the best response from the follower is to play his best response for the game induced by this signal. In this way, the leader can guarantee himself an average utility per round that is at least his utility in the public signaling game. So intuitively, the signaling scheme gives the optimal trade-off between using information in the short term and saving it for the long term. So basically, the information that is used in the short term is entirely captured by the signal, sigma. Okay, back to our example. So suppose the realized state of nature is 1, 2. So basically, these 2 bags of money are allocated to the first 2 bank. Then the soldier will invoke the signaling scheme. So that with probability x, the soldier will act as if the signal is sigma 1. So that the soldier will defend the first bank with probability x, and then defend the second bank with probability 1 minus x repeatedly. And with the remaining probability 1 minus x, the soldier will act as if the signal is sigma 2. So that the soldier will defend the second bank with probability x and defend the third bank with probability 1 minus x. Now we see that with some positive probability, the defender will defend a bank actually without money. So in this way, the soldier can mislead the attacker and benefit himself. So we also notice that the attacker's utility is 1 minus x, which is strictly larger than 1/3, which is the attacker's utility when the game has only 1 round. So this is because the attacker can benefit from repeated interactions. Because in a repeated game, the attackers can observe the defender's historical plays, which gives the attackers more information. Okay, now we have established the strategy for the leader. So how about the follower? However, to establish a strategy for the follower, we cannot rely on the public signaling scheme. Because in the public signaling game, we have a credible principal who commit to a public signaling scheme. However, in the Bayesian repeated game, there is no credible principle. And in fact, the leader is also strategic. As a result, the leader may deviate from the signaling scheme. Therefore, the strategy of the follower can only depend on the prior as well as the leader's historical plays. And the construction is quite involved and is based on the Blackwell's approachability argument. An interested audience is encouraged to look at our papers for further details. The main lesson we learned from this equivalence is that repeated plays prevent the leader's deviation from the signaling scheme, because any signal will be called ultimately, resulting in suboptimal utility for the leader in the long run. In addition, we also made this equivalence algorithmic. We already show you how to construct the leader's strategy from the signaling scheme, and we also show you that their game value are in fact the same. In the paper, we further showed how to construct the follower's strategy efficiently from the game value. Okay, this wraps up our story for the Bayesian repeated games with its exogenous states. Next, we are going to look at Bayesian repeated games with endogenous states. So the main difference here is that now the states of the nature, its distribution is chosen by the informed player, the leader. Which means that now the leader can determine the prior information Okay. Now, to better demonstrate this new model, let's take a look at the example. So we are in the same security game basically. Now, the soldier can, in addition, determine the allocation of the money. So let's see what happens if this game is one shot. And when the game is one shot, actually the optimal strategy for the defender is quite straightforward. So basically, the defender will assign the soldier to one bag of money deterministically. And then these two bags of money are uniformly are distributed uniformly at random. So now from the perspective of the fifth, so each bank again looks the same. So each bank is undefended with money with probability 1/3. So far so good. Actually, the key lesson we learn from this strategy is that when the game is one shot, then correlating the allocation of the money and the allocation of the soldier, the defense, will be beneficial for the leader. So what happens if the game is repeated? So it turns out that this is the optimal strategy for the defender. Actually, we already see these pictures before, which is correspond to the posterior for signal sigma 1. So basically, in this strategy, the defender will allocate one bag of money deterministically to the first bank, and then for the second bag of money, it will allocate to the second bank with probability x, and then allocate it to the third bank with probability 1 minus x. As for the defender will defend the first bank with probability x and defend the second bank with probability 1 minus x repeatedly. And notice that this defender's strategy is independent of the realization of the allocation of the money. So which means that no matter whether the second bank of money is allocated to the second bank or the third bank, the defender's strategy remains the same. So in this strategy, we know that the fifth utility again is 1 minus x, so which is the same as the setting with exogenous states. But this is mainly because the uniform prior is special. So in general, the fifth utility would be smaller in the setting with endogenous states, because in this setting, the defender has more power. Okay, so the key property of this strategy is the following. So basically, since the soldier used the same strategy, same defensive strategy repeatedly, which is independent of the allocation of the money, so basically no information is leaked during the gameplay. So the attacker learns nothing from the soldier's allocation. So it turns out that this is not a coincidence. And actually, our second contribution is showing that the Bayesian repeated games with endogenous states is equivalent to team max-min games. And again, team max-min game is a one-shot game. So we once again reduce a multi-round game to a one-round game and show their equivalence. And we further made this equivalence algorithmic. So what is team max-min game? So in team max-min game, again, we have one more player, the theta player, who control the distribution of the states. And in this game, neither the leader nor the follower can observe the actual state that is being sampled. So in this game, all these three players choose their strategy simultaneously. And the reason why this game is called team max-min game is because the theta player and the leader form a team so that they share the same utility. And again, the follower's utility is simply the opposite of the leader's utility. So with this team max-min game, it's quite straightforward to construct the leader's strategy in the Bayesian repeated game. So basically, given the Nash equilibrium strategy profile for the team max-min game, then the leader will set the distribution of the states according to the theta player's strategy. And then each round, he will use his equilibrium strategy in the team max-min game. And in this way, we can observe that the follower basically learns nothing about the prior as well as the realized states of nature from the leader's strategy. As a result, the best response from the follower is to play his equilibrium strategy in the team max-min game. Okay. So however, again, it's not straightforward to construct the strategy from the follower. And actually, in this case, we are facing one more obstacle because Now there is no prior. The prior is controlled by the leader. As a result, the follower strategy can only depend on the leader's historical plate. However, we still managed to construct the follower strategy, and interested audience are encouraged to look at our papers for further details. And the key lesson we learned from this equivalence is that due to repeated plays, then correlating the prior and the defender's strategy per round is no longer beneficial in the long term. Okay, we also made the equivalence algorithmic. So we also give an efficient algorithm to construct the follower strategy given the game value. And combining with the algorithmic reductions for the Bayesian repeated games for the exogenous states, we have pretty complete pictures about their computational complexity. And in addition, we also show that the team max min game is computationally easier than the public signaling game. In this sense, we show that the Bayesian repeated games with endogenous states is computationally easier than Bayesian repeated games with exogenous states. As a conclusion, so in this paper, we study Bayesian repeated games with exogenous and with endogenous states. We demonstrate their equivalence to the corresponding one-shot game. We also made this equivalence algorithmic. As an application to security games, we also investigate their computational complexity when the base game is security games. And it turns out that even in the simplest settings, it's MP hard to compute the game value for the Bayesian repeated games with exogenous states. For the Bayesian repeated games with endogenous states, a more nuanced picture emerges. We provide an almost complete picture about the relationship of the computational complexity. Okay, then that's it. Thank you for your attention.